everyone. In this chapter we will discuss about the direct design. Outline of this course start by introduction, root locus method, frequency response, and analytical design. If you remember, many times we discussed about this system. If you have the system such as the GIS, you can easily directly control by the CS by the different method that before you remember we discussed about the root locus design, and this system easily can change to the discrete time by the GZ, and the control can easily go to the CSZ, and we have two ways to design. One time you can design the CS, then change to the CZ, and the GS go to the GZ, that you learn about the method about the discretization. Or directly you can design about the CS here, directly to CZ, or from here we with the Z domain design the CZ. We check together. We have the EAT, the time we take the sample time of here become E star T. This is the controller, and this is a data holder. Digital control, the meaning about this rectangle, that means the controller plus the holder. Objective is design a distinct control that satisfies some specification. Emulation design, they show such as here you have the CS and the GS system. Design a continuous control C with the root locus or frequency method. Discretize the controller, zero pole matching method, or the testing with the pre-wrapping, any method that you can design. And the work well when the sample time is small enough. Why? Because if the sample is very small, that means the continuous and the discrete will be similar together. This is the indirect. First I want to design this, then change this one to the CSZ by this method. Another thing, direct design, that means you have the GZ with the holder and the GP become G star S or the GZ, and you directly design about the controller here. The sample size is taken into the account in the design, so this method can work for the large sample time too, because that's a meaning first you design about the CS, then you go to CZ. This one T sample should be small, but for the direct design sample time you can increase the big number too. Here they show the if you have a C star S or the CSZ, if you have a GZ here, the output of my system will be C star multiplied by the GP multiplied by E star, because here is a E star, and I know the ES become RS minus YS. And if you have a sampler, this side YS will be CS multiply here multiply E star S, and the ES will be R star S, because RS here will be R star here, minus Y star here, because here become YS. Take the sample, become Y star S. That's the two different shapes. The following equivalent discrete diagram will be used in this chapter. That means you have the CSZ, GPZ. That means GPZ is include about the holder and the GS. Alright, the hold. Then the transfer function about my system closed loop becomes CZ GZ 1 plus CZ Z when you have a negative feedback. Now, little bit we will remind about the root locus in the S domain and the Z domain. How can we draw the root locus of the following discrete time, and is the root locus of the GA2 different from the root locus of the continuous time? I put the exactly about the S to the Z. I want to know about the what's the difference between root locus about the G1 and the GA2. This becomes the GA1, S plus 3, S plus 1, S plus 2. Here become the Z plus 3, Z plus 1, Z plus 2. If you see, the root locus will not change anything when implement about the 8 rules that we saw in the EE312. First 5 rules to sketch the root locus and the 3 rules for refine the sketch. First is the number of the branch, is a symmetric, real axis segment, starting and ending point, behavior at infinity, and the 3-1 is a real axis breakaway and break-even, finding j omega axis crossing, and angular of the departure and arrivals. We start by example number 1. Consider the negative feedback given with the following: the GA2 is Z plus 1, Z plus 3, Z plus 2. If you remember, you have the 1, 0 here, 2 pole here, minus 1 and minus 2. If I draw this one of them is a minus 1, I show by cross is a pole, minus 2 and 1, 0 here. If you see, 2 pole you have 1, 0, one of the pole go to the 0, another pole you go to infinity. That means 1 infinity 0 and 1 infinity branch, and 1 infinity 0 you have, because this pole go to this 0, this pole go to infinity to find the 0. Root locus area we put the name 1, 2, 3, and if you remember, this minus 1, this minus 2, this minus 3, I put the 1, 2, 3 number. If the odd number we start from here will be on root locus. If I reach to the even number will be not on locus. I reach to the odd number will be on root locus. That's why I said minus infinity until minus 3, minus 2 to minus 1 will be on root locus. If you remember, the asymptotes become the pole minus about the 0, divide about the number about the pole minus number about the 0. Here will be 0. And theta, or the theta about here, become 2k plus 1, 180 degrees divided by the number about pole, number about 0, become 180 degrees. That means here asymptotes the point here and 180 degrees there. If you remember the finding about the k, I write the k, hz, gz, and I multiply here, then you find the k, z plus 3, and extend about the denominator, and change the z to the sigma, and take the d k by d sigma equal to 0. Then we will find the denominator equal to the 0. You find the sigma equal to minus 3 plus minus radical 2. This one about the breaking point. And if you substitute in the previous equation, you find the k2. Okay. Now, as we saw together, we have the minus 1 here, minus 2 here, and 0 minus 3 here. That means these two poles we will break from here. They go up, go one of them here, one of them reach to the 1, 0, another one go here, and they go to infinity. And this point, the breakaway and the break in, calculatable by the k that we saw together. One of them become minus 1.8, another one become minus 4.42, because you find the two root about the sigma when you find the k. Example number 2, consider the negative feedback with the following system. GAP here, they have a 3 pole. Determine the range of stability for the k. Okay, first for the writing about the root locus, you have the 3 pole, you have a 3 branch, you have a symmetric, and you have a 3 pole, you don't have a 0 actually. That means this 3 infinity 0 you have. That means this 3 pole you go to find the infinity 0. One of them is z equal to 0.5 is here, one of them is a minus 1.2, and one of them is here. If you put the number 1, 2, 3 between minus infinity and minus 1.21 here, and another one is a minus 0.1, and here becomes 0.5 here. Here become the sum of the pole minus sum of the 0 divided by the number about the pole minus number about the 0. You don't have the 0 here, will become 0, and here become number about the pole, you have 3, and here the sum of about the pole become minus 0.27. that means around here. If you find the angular become 180 degrees and minus 180 degrees, and if you consider these two poles close together will be break, and one of them go up, one of them go down, and here is 180 degree will go here, and this circle about in the z domain about my area. The closed loop system always unstable because the red branch is always outside of the unit circle. If you see this is out of my circle, and your system become unstable. This pole here. Need to design about the lead, lag, and or the PID controller. Here they find about the breakaway and the break-in by finding the k. That means you must find the k, HZ, and the GZ. Here HZ is a 1, and you write about here. You find this formula Z. You go to the sigma, and then you find the dk by d sigma equal to 0. You find the two root, and you find the breakaway and break in. But based on this, you find the two root. One of the root will not accept it because they are not on the root locus. This one will not acceptable, and this one will be acceptable. If you see here, this point will be about your break away system. Now we go to general design.